afternoon and welcome to another live stream. Hopefully I'm going to be able to be coming to you nice and loud and clear, and we're going to learn something about 3D Pythagoras and 3D trigonometry this afternoon. This is a topic that I know a lot of people can get confused on, but I'm hoping the things I'm going to show you will allow it to make a lot more sense, and if that is the case, will allow you to work through problems and work through questions. I plan to add some questions at the end of the lesson. I'll add them to the description that you can then go away and do. Maybe you want to use my maths or Cuboids maths, but I will try and find some questions that are relevant to this and add them to the description. So first of all, I just thought I'd mention to you, I was doing some research the other day on the best way, because obviously people are stuck at home now and they're not sure where they're going to be doing with their careers. Some of you might be year 11, some of you might be year 10s, but once a good career choice is especially if you're struggling to get your grades up, is scuba diver. Because apparently, in order to be a scuba diver, you just have to keep all your grades below a sea level. Yeah, I've probably lost all the people that were watching live. And anyone who is still with me, I have got with me a cardboard box. And I'm hoping the cardboard box will help with everything I'm going to talk about today. Because the main questions I'm going to talk about are where we've got a cuboid. And as you can see, I've already drawn a line going up there. And the nature of it being three-dimensional is imagining within this cuboid, you place the ruler from one corner to the opposite corner. So almost down that sort of one finger to one finger. And it can rotate around there. And what I'm going to try and do is show you how we can visualize this to make these questions easier. First of all, we're going to look at it from a Pythagoras perspective. Then we're going to look at it from the perspective of trigonometry and how we can look at the angles of elevation. Because that's useful for things like aiming and targeting. It's useful for working out the angles between different reinforcements and different forces for, let's say, a suspension bridge and things like that. So I'm going to just flip into here, and hopefully now you're here, you'll be able to see my 3D trigonometry, and I'm going to start with a very simple rectangle. And from that rectangle, I'm going to turn it into a 3D shape by adding a few lines. And like so. And we're going to give it some measurements. And the measurements we're going to give it are 6 meters, 2 meters, and 3 meters. So it's got a depth of 3 meters, it's got a height of 2 meters, and it's got a width of 6 meters. What this means is, the questions that we're talking about might say, if this is going to be A, B, C, D, and then we could imagine in the background, imagine this is a glass container, maybe it's a very large fish tank, which is apparently very empty and devoid of water at the moment, and then we've got E, F, G, and H, and it asks us to find AG. Find the length of AG. And AG is here, but if you imagine inside this container, it's going from the top corner, behind all that stuff, to the far corner there. And to do that, I think it's useful to imagine looking top down in the box. And to show you what it would say it'd be like top down, we'll just draw it. This is a top down view. It isn't, but now it is. That orange line there, no, green. That orange line there, and we can't see anything behind it. If we look above, we've got this shape going on. And we're only aware of the 6 and the 3. The 2 has disappeared. But if we now look sideways on, that is creating like a shape, a flat shape within the box itself like it's called a plane. It's a separate 2D shape which is within the box itself. And by doing that, that plane is a triangle of itself. So I'm going to write in here that just this plane is going to be this distance along the bottom, because that's what it looks like top down, and it's going to be up the side, we know it's 2, and that's the side we want to find, AC. So we need to find x first, but we've got the ability to do that because we've got that x squared by Pythagoras is 3 squared plus 6 squared. So we end up with 9 plus 36 is 45. And the next step is we know that x must therefore be root 45. But notice, I am not going to write down what that is. And that is because I'm going to put this in this inside. You notice I've got this triangle. This is the shaded triangle within the middle of my cuboid. This is root 45. And I do that because my second round, this is my first round of calculations, my second round of calculations uses the AC squared equals 2 squared plus root 45 squared. And hopefully this will make it clear why I didn't bother finding out what the square root of 45. I'd lose some rounding errors because the square root of 45 squared is 45. So AC squared equals this, and therefore AC squared equals 49. And we now have AC is the square root of 49. AC equals 7. So we can see in the very rare scenario that when it's like this, in a 2, 3, 6, you do actually get a whole number for AG. It's 7 centimetres. It's rare that it would be a whole number, but by keeping that as root 45, squaring it and it coming back out. Now, it may be the case that some of you are aware that there is a shortcut. In 3D Pythagoras, if you're dealing with a cuboid, and the reason I'm telling you if it's a cuboid, because sometimes it won't be. We'll talk about a pyramid in a second. In the case of a cuboid, though, there is a new version of Pythagoras which states that a squared plus b squared plus c squared equals d squared. Therefore, to find d, you can do the square root of the length, add the width, add the depth. It's like a different formula for cuboids. Now, I prefer what I've done here in orange purely because it applies in lots of different types of questions, because you're gonna need diagrams. One of the biggest bugbears I have with the students I teach is trying to explain to them that you need to have diagrams to support and help you to see quite what you have to do, and I'm sure some of you are here. So anyone who's here to come and look at Foundation Year 10, the foundation stuff I did earlier applies to the Foundation GCSE. I'm going to be doing different foundation stuff. Thank you for joining. This might still be useful, but the foundation topics are all in the foundation section. Feel free to email me and request anything, or if you want to just leave a comment and request a certain video in the foundation channel, I will happily do the foundation topics there. Okay, the next thing I'm going to do is scroll down slightly. I did mention it changes slightly when we're talking about a pyramid. Here we have a square-based pyramid, and we'll try and make it work like it's invisible. It's not the best one, but you can see what's going on. Probably be better if I'd had the line up there. In fact, I'm going to change it so that you can all see that that works. Okay, we've got a square-based pyramid. In this square-based pyramid, because it's square-based, I've got 6 and 6. And the height is going to be the distance from the middle bit here. And imagine having a bit of thread dropping directly down. And it goes exactly into the middle of the pyramid. So we've got that there. Now, just as before, we can create like a slice of this diagram here to work out a different thing. So in this case, I'm going to work out a slice going out towards the edge, because you would probably be given the slant height or slope height, or you'll be given the height of the pyramid. It could be given either. You might be given the height and asked to find this slope, and the slope could be the slope in a straight line, or it could be the slope at the edge. Again, a lot of it will depend on letters that you're given around the edge. And this one says find the height of the pyramid if ED equals 7 centimetres. So we'll note that down, and that would be 7 because it's a square based. What we've got is another orange wedge. Sorry, Abdullah. In the previous question, the D means the distance diagonally across from one corner of the cuboid to the other corner of the cuboid. So if you're trying to get diagonally across from one corner to the other, that is the distance D, and it's equal to the length, width and depth. I do apologise for not noticing your question. Hi, Kieran. Okay, so we've now got a wedge here, which again allows us to work out things if we draw it out separately from the question, which is why I like using different colours, because this is now a right-angled triangle with height 7 and a distance, which I'm going to call x again. If only there was a way of finding x. Looks like there might be. There's two ways of doing it, but I can see on the bottom that this here would connect to the middle by 3 and 3. If it's 6 across, then halfway has to be 3 and halfway has to be 3. So we've got a new triangle on the bottom. Remember, the 3D Pythagoras is always going to involve two triangles. So we've got 3 squared and 3 squared giving us x squared. I believe 3 squared is 9 times 2 is going to be 18. So that's going to be root 18. And once again, I'm not going to work out what root 18 is. I'm just going to say that that's root 18. Therefore, for this one, we've got a takeaway version of the Pythagoras theorem. We've got 7 squared equals h squared plus root 18 squared. Remembering that when you square a root, it goes back to being 18. So 7 squared equals h squared plus 18. And then we subtract 18 from both sides. That's 49 minus 18 is 41. 31 equals h squared. So h will be the root of 31, which is going to approximately be 5.5, but let's just verify exactly what it says it is. 5.6 to 1 dp. So, any questions about that at all? Abdullah, Kieran? Anyone else who's got any questions? No? Okay. So hopefully that's been useful so far, and we can see it's all about finding a wedge or 2D shape within the 3D shape that we then draw out separately. There isn't a formula for other shapes that aren't cuboids. We could make one, but you'd have to make one for every single shape we do. So rather than that, it's better to try and visualize, again, looking top down at the shape you're dealing with and drawing a 2D representation makes it much more easy to work out the two triangles that are going to be needed for 3D Pythagoras. That takes us halfway. If you're only here for 3D Pythagoras, then fair enough. If you're ready for some 3D trig, Then we're going to do the same. We're going to go back into drawing a cuboid, because I wanted to do it as two separate things so that we kept the same bits together. I don't want to show training, thank you. I want to draw from there to there, there to there, there to there. Not the neatest straight lines, Mr. Harris. Imagine it was neat straight lines, and we've got 5 centimetres, and we've got 14 centimetres and 3 centimetres. And the same as before, we've got A, B, C, D, and we've got our fish tank effect. And again, this one says, what is the, and it's got an E, F, G, H. But it wants to know let's just try and get this out of the way. I do apologise. What is the distance, the angle DEC? To do that, again, I'm going to need to visualise what DEC is talking about. So I'm going to see if I can draw a straight line, DE, and indeed EC. And once again, I have this right-angled triangle wedge. So I'm going to draw it and label the sides that are useful, D, E, and C. I know that that is 3, but I don't currently know that or that. So we're going to need a little bit of the Pythagoras we've already talked about to get in the position where trigonometry is going to allow us to work out this angle theta. Remembering, in trigonometry we only need 2 sides in an angle, so it doesn't matter which one we work out. For that reason, I like to imagine looking top down, and there's my eyeball. Bit scary. Didn't know I had green eyes, did you? Okay, looking straight down, you can see the line in the middle, and I think that gives us something like this. And the 14 is on the side, and the 5 is on that side, and we wanted to find that side there, and that side we're going to call X, and so therefore that side represents that side there, so we'll get rid of everything else that's not useful. That question mark's not useful, that little dot is not useful, that line was. It'll come back. We don't need that bit. Could argue that the base of the triangle is quite important. So this is now looking top down to get X, so we can then feed it back in there. So we're going to use a Pythagoras. 5 squared plus 14 squared is 25 plus 196 is 221. Root 221 is approximately 14.9, but let's just get that right. 14.8, but 89. But I'm again not going to use that. I'm going to use root 221 in my answer. I'm going to put this as root 221, so it's the exact answer I need. And I now go through the standard steps you would do if you were doing a normal trigonometry question. Label the sides. I have adjacent, I have opposite, and I don't have the hypotenuse, so I'm going to cross it out. I want to then find this angle using O and A. So thinking of SOHCAHTOA, I'll write SOHCAHTOA. And I don't know how your teachers have taught you this, but that's the way I teach you, just SOHCAHTOA. Write it out, work out the one you need. We need TOA, which tells us to draw tan theta is O over A. T-O-A. We put our finger over the thing we want. To make it cleaner, I'll put some yellow highlighter. We want the angle. So we're going to put our highlighted finger, my fingers are clearly made of highlighter, over that. And that tells us to do O over A, which means I can then write, not in the highlighter, tan theta equals, excuse me, equals 3 over root 221. So we then need to get rid of tan, and the way we get rid of tan is to use tan to the minus 1. So theta equals tan to the minus 1 of 3 over 221, root 221, is equal to 11.4 degrees. And what I like to do is whenever I do a question like this, I think, is that reasonable? Well, if this is about 14.9 and this is only 3, that's quite long compared to its height, which says to me, just a second, it says to me, if you've got something that's really long but not very high, the angle of elevation is unlikely to be particularly big. So it's going to make it from a long thing very likely to be less of an angle. If this was more of a square, so 3 by 3, it would be elevated much more in order to get that same distance. So you can see, using your arms, I guess, that when you've got a long thing, it's going to need less elevation than when you've got... It's not sounding particularly good, is it? When you've got a long thing, it needs less elevation. When your cuboid is fairly long, but not particularly high, the elevation is going to be less. But you'll notice a common theme in what I've been trying to explain to you here, and that is the fact that you need 2 steps. You needed a step to find the missing side, and then you needed a step to find the angle. There might be questions where it gets skipped out. You only need to find the angle because they put all the numbers in, but finding which numbers is needed is difficult. Hence, I always draw a plane within the shape of where I want to be working. And I would hope that that's helpful. Okay. Everyone happy with what it was saying? Abdullah seems to be following. If anyone has any questions, then that's fantastic, and that's fine. This is basically how you work out trigonometry within a 3D shape. I hope it's been useful. If there are any questions, either put them in the comments or email me at schoolofmrharris@gmail.com. I hope it's been useful. Until tomorrow, and not tomorrow, tomorrow's Saturday. Oh, brilliant. I'm going to be doing a board game workshop this weekend, so I'm going to put a video notice up on for probably Sunday, where I'm going to do a thing where we're going to design a board game together. As people know, some people know I'm a board game designer as well as a maths teacher. So we're going to do a little board game workshop. I'm going to invite various people to help us out, and we're going to talk about board games and board game development. If you're interested in that, or might be interested in watching that, it won't be a long video, but I'll put something about that later in the week. If not, then until Monday, when we're going to talk about something else that people can ask me about, just let me know what you'd like to go through, and I'll try and do a video on it. Thank you very much for watching. Feel free to like and subscribe, and I'll speak to you next week.